Okay, so next we're going to go over this question over here. So this is one from the exercise sheet, and it's one we've done before, but I wanted to go over it again because I wanted to mention something important. So the question asks us to prove that this language is not regular, as before. And so, like always, we want to do this using the pumping lemma by contradiction. So we're going to assume that the language is regular, which tells us the pumping lemma should hold or it must hold, but then show that that actually isn't the case for some string in the language. So first let's go over what the language is. So it's all strings over alphabet 0 and 1, where the number of zeros at the start of the string is more than the number of ones at the end of the string. So for example, this would be in the language because there's more zeros at the start than ones at the end. But this wouldn't be in the language because the number of zeros is the same, and we need there to be more zeros than ones. Let's go over the proof. We want to prove it's not regular, therefore we assume it is and proceed by contradiction. So assume towards contradiction that L is regular. Because it's regular, the pumping lemma should hold. So therefore, pumping lemma must hold for L. Because we know the pumping lemma must hold, then by the pumping lemma, there has to exist a pumping length. Also, I'm writing on the boilerplate now, but in the future, I'm just going to copy paste it because I can't be asked. So pumping length n greater than equal to 1. Remember, it's greater than equal to 1 because the pumping length represents the number of states in the hypothetical DFA for this language. And a DFA must have at least one state, and so the pumping length also must be at least 1. So there exists a pumping length such that for any string that is in the language, any string W in L, where the length of the string is at least a pumping length, which is n. Oh, what the hell? Did not mean to do that. Um, okay. For any string W and L where the length is at least n, there exists a breakdown W equals to XYZ. And just to reiterate one more time, if a string is in the language and its length is at least n, so I mean if its length is at least n, then by the pigeonhole principle, if a DFA reads in this string, it will encounter the same state twice. And if it encounters the same state twice, then there is some loop within a DFA. And therefore we can break the string down into 3 parts. The part before the loop happens, the part that causes the loop, and the part after the loop happens. So this is guaranteed because of this thing over here, which like invokes the pigeonhole principle. Okay, so we can break it down into 3 parts such that 3 pumping lemma properties hold. Let me just make this neater. Okay, the first property is that, as we said, there must be a loop within the DFA. And so the part of the string that causes the loop cannot be empty, because it must exist. The second property is that the loop must happen within the first n characters being read. And so the length of the string up until the end of the part that causes the loop must be at most n. And the last property is that no matter how many times we skip or repeat the part that causes the loop, we should still end up in the same state, ending state at the end, which has to be the except state because the string is in the language. And so no matter how many times we skip or repeat the loop, the string should still be in the language. Okay, that's the boilerplate. Now we're going to move on to the proof. As before, our goal is to select a string within a language that has at least length n, where there does not exist a breakdown where these three properties hold. So no matter how you break it down, something goes wrong. Now the most important thing to keep in mind is that this is the most important part of the proof. We can't just select any string, we have to select one that will lead us to a contradiction. And some strings won't do that. So some strings do in fact have a way of breaking it down where this happens. An example of such a string for this language would be this one. So you might think that this is a good string to select because it's in the language and the length is at least n, right? So it's in the language because we have more zeros at the start than ones at the end. So W is an L, and the length of W is going to be 4n, which is greater than or equal to n. Sorry, this is a 3. Looks a bit weird, so let me just rewrite it. Okay, so this is satisfied, and so the pumping lemma tells us that there must exist a breakdown. Then in the proof, we want to show that there does not exist a breakdown. But this would be impossible for this string, because there does in fact exist a breakdown. And let me show you one such breakdown. We could let x be epsilon. We could let y be 0 to the n, so n zeros. Or we could let z be the rest of the string. So that would be 0, 2n, 1n. So altogether, x, y, z will be epsilon, 0n, 0, 2n, and 1n. And this is just the same as 0, 3n, 1n, which is the string we had before. So that's one way of breaking down the string. And my claim is that this satisfies all of these properties. Well, first, let's look at the first one. Y must not be empty. Well, Y isn't empty, so the first property is satisfied. Next, we need that X and Y has length at most n. Well, X and Y is just epsilon 0 n. The length of this is n, and so this property is also satisfied. The next property is about the pumping. So this one says that we can either remove y from the string, or repeat it any number of times, and the resulting string will still be in the language. So let's see what happens if we pump down. So if we remove y, well, that will give us epsilon 0, 2n, 1n. So we've just removed this. And is this still in the language? Well, it is, because there's more zeros at the start than ones at the end, right? So pumping down won't lead us to a contradiction. Let's see what happens if we pump up. Sorry, there was supposed to be a z over here, my bad. Okay, if we pump up, we're just adding repetitions of this to the start of the string. So we're just adding more zeros to the start. And if we keep adding more zeros to the start, we're never going to encounter a situation where the string is no longer in the language. And so we will never reach a contradiction. So therefore, for this string, there does in fact exist a breakdown, and so we can't reach a contradiction. So we couldn't have used the string to prove the language is not regular, because there's no contradiction to be made. So this is a bad string to choose. And so you might be asking, what's a good string to choose? Well, in general, you should try to choose strings that are like on the boundary of being in the language. So just barely acceptable. So for instance, if we had n ones in the string, we would want to try and make the string just barely in the language. So we could make it so there's just barely more zeros than ones. So n plus 1 zeros. there's only one more zeros than ones, and so this is barely in the language. Okay, so we know W is in the language, and we know that the length of W is at least n, because the length of W is 2n plus 1, which is greater than or equal to n. And so we know that the pumping lemma properties should hold. So there should exist a breakdown where these three things are true, and we're going to show that this is in fact not true and that there is no way of breaking it down where the pumping lemma properties hold. So first thing to note is that as before, because we set the first n characters of the string to be all zeros, so the first n plus 1 characters are zeros, x and y can only contain zeros as well, because the length of xy is at most n. So if we have this, sorry, I'm a tiny bit sick. So if we have this string and we try to break it down into three parts, x and y has to be somewhere over here because the length of xy is at most n. So therefore, x and y contain all zeros. So by property 2, contains only zeros. And then by property 1, y cannot be empty. So if xy contains only zeros, then y must also contain at least one zero because it's not empty. So by property 1, y contains at least one zero. So y equals to 0k for some k greater than or equal to 1. So this just says that y has some number of zeros. Okay, so we've reasoned about what the breakdowns can be. So no matter how you break down the string, wait, let me just add that to the proof. So no matter how you break down, so no matter how you break down W, this stuff will always be the case. So next we want to arrive at some contradiction by pumping the string. So first let's think about what happens if we pump up. We will just be adding more repetitions of y to the middle of the string. And because y just contains some number of zeros, we're just adding zeros to the start. And if you were to add zeros to the start of the string, it would still be in the language. So pumping up wouldn't lead us to any contradictions. And so we can't pump up, right? We need to think about some other way of doing it. So we can try pumping down. What happens if we remove y from the string entirely? Well, we would be removing this from the string. We'd be removing some number of zeros, right? So by pumping down, so x, y, 0, z will be what? So it will be this string, but without this part. So we're removing k zeros from the string. And so if we had n plus 1 zeros before, and then we removed k zeros, we will now have n plus 1 minus k zeros. So x, y, 0, z, which is the thing we get by bumping down, will be this. So it'll be n plus 1 minus k zeros, and the same number of ones, because y had no ones inside of it. So is this still in the language? Well, let's see. The language required us to have more zeros than ones at the start. So the language wants this to be greater than n, but that's not greater than n. Let's take a look. So n plus 1 minus k. This is not greater than n. Why? Because k is at least 1, as we mentioned earlier, over here. K is at least 1. And so if we have n plus 1 minus k, which is at least 1, then this entire thing will have to be at most n, because this 1 gets cancelled out by the k, but k might also be greater than 1. So this entire thing will be at most n. So in the best case, k is equal to 1, which makes this thing equal to n. But in the worst case, k is more than 1. And so this entire thing has to be at most n. So therefore, n plus 1 minus k is not greater than n. And so that means this string has less zeros at the start than ones at the end. So therefore, x, y, 0, z is not in the language. But this property over here told us that it should be in the language. And so we've reached a contradiction, which contradicts property 3. So therefore, by contradiction, L is not regular. Okay, so the main takeaways of this question are that you need to select a string that does lead to a contradiction. Not all strings will. The other thing to keep in mind is that sometimes pumping up will not work and you have to pump down to reach a contradiction. Okay, that's it. If something wasn't clear, just let me know. I can explain it again. And I'm going to go on to the next question now.